We'll hear Troels Harmark talk about gravitational solitons and non-relativistic string theory, please.
Yeah, thank you. I should say apologies in advance because I woke up with a major cold, but I hope it will not interfere. Let me see how this works. Yeah, I will talk today mainly about this work here, but it will also be related to, and this is with Johannes Lahnsteiner and Niels Obers, but it's also highly related to some previous work, and it's highly related to Siggy's beautiful talk as well. Let me see if this works. Yes, all right. So just a very sort of broad introductory slides. So I think, of course, since we are at Eurostrings, we would all like to understand quantum gravity. And this is sort of where you unify relativity and quantum mechanics and gravity all in one beautiful package. But it's not super easy to understand. So one can take certain limits and try to get a better handle on things. And one of the interesting limits one can take is to take the speed of light to infinity. So you get rid of relativity and instead do non-relativistic quantum gravity. And then maybe you can learn something about quantum gravity, which is hard to do in the full theory. So a way to approach non-relativistic quantum gravity is to consider certain BPS modes in string theory. This might seem surprising if you haven't thought about this, but you can start with basically just flat space, but with a circle, and then you could take a BPS state where you have corresponding to momentum along that circle. If you now want to focus on modes that lie just above this BPS state, that's what I tried to illustrate on this energy ladder here. So you want to focus on modes that are near BPS, where this W is sort of the quantized momentum. Then you can do that by changing coordinates that focus on energies that are really close to this BPS state. So if you do this coordinate transformation, then you can see that you get the energy minus the BPS energy. And then if you take C to infinity, then you basically take a decoupling limit that really decouples these modes from all the higher lying inner modes. And this is actually nothing but a DLCQ limit, which is famous also from, for example, the BFSS matrix theory story, etc. And one of the weird things of BFSS is that it somewhat seems to involve compactifying a null direction. And this has sort of given it a little bit a slightly bad reputation that it seems a bit a singular or not really, geometrically not really very well-defined limit. However, if you take a T-duality along this compact direction before you take C to infinity, then you can then you get this background instead with a critical electric B field, and now the C going to infinity limit has transformed itself to the so-called non-relativistic string theory limit, in this case in flat space. And here you can actually, as I will show you in a moment, make sense of the geometry. The point is just, it's not geometry as we know it, but it's a non-Lorentzian geometry. So basically, zooming into this BPS point give you non-Lorentzian geometry, and that's also the what Siggy was telling you. This was the story 25 years ago. Since then, we have learned a bit more about how to take this limit more generally, not just in sort of around flat space, but you can also do it basically in a general curved background. So there's some details here, but it's not so important, the details, how you formulate this. That's more like if you really want to work with it. But the point is that you split the metric and the Kalbormon field in a longitudinal part and a transverse part, such that the longitudinal part is designed to give you a critical electrical B field when you take C to infinity. And if you do that, then you can take your favorite relativistic string Nambu-Goto action and take this limit, and then you get a finite answer, which is this. And again, the details are not so important. It's more a sort of a message that it gives a finite action. But this action is no longer with a relativistic target space. It's with a non-relativistic target space. The so-called torsional string Newton-Cancang geometry. And the point here is that you split up the longitudinal part and the transverse part, and then you even get a part from the Kalbormon field that all goes together in some beautiful geometric package that you call torsional string Newton-Cancang geometry. And among other things, you can see that the speed of light is actually infinite in this transverse space, and you get some Galilei-type boost that makes the part with the longitudinal and the part with the transverse written here. So this is a new geometry which is not relativistic. So this above limit is quite amazing, but it has also some limitations, or it hides some crucial things, because it's not for sure that any string background you want to look at, relativistic string background you want to look at, actually fit into this limit. So this was one of our motivations for our study, that we wanted to try to take actual gravitational solitons of relativistic string theory and see if we could take this limit. And probably I don't have to say this, but gravitational solitons are quite important in string theory. We have been recognized that for the last 35 years or so. So they're consistent, give you consistent target space backgrounds of string theory. You can use it to study certain non-perturbative physics of string theory, halography, obviously, and also thermal physics. You can learn about with, say, black brains, for example, or black holes. So let's see how you can find gravitational solitons in non-relativistic string theory. So we were, in a way, very simple-minded about it. We simply wanted to try to repeat the procedure that was done in flat space, but now for curved backgrounds. So we considered a particular class of solitons for which you have a Poincaré, 1+1 dimensional Poincaré symmetry along the directions are here called T and X. And this is what we think of as the longitudinal part of the solution. And then we do this coordinate transformation that was also on one of the first slides. And we do a T-duality after the coordinate transformation. Then we should get a finite C soliton that should have the correct scaling in C in this coordinate, in this parameter we take to infinity. And then we finally take c to infinity, and then we should get the gravitational soliton. And this works quite well, at least in some cases. So if you take a dp plus 1 brane, again, the details are not super important here, but it's just to show you something. So plus 1 is for this direction big X here, because we want this 1 plus 1 dimensional Poincaré symmetry of the D brane. So here we have 1 plus 1 dimensional Poincaré symmetry. Then we do this solution generating technique, and out comes a non-relativistic string theory geometry, which looks like this. And since you have to do a T-duality along the way, this dp plus 1 actually become a dp brane in non-relativistic string theory, which is now smeared along this direction v, which is longitudinal to the strings. So actually this is, in a sense, a transverse dp brane because it doesn't share this v direction with the string. And this was also sort of predicted that this solution should exist from open string point of view, at least in the probe limit, but this is in the back-reacted, this is for the back-reacted dp brane. That was not found before. And after our paper, Chris Blair figured that this actually is a half BPS solution in non-relativistic string theory. Then, since we know of the importance of gravitational solitons, we can try to think of some of the same things we have been doing in relativistic string theory. So one thing is to take a near horizon limit, and the cartoon version of a near horizon limit is simply just to say that this part here blows up so that you emit the one. And that is what gives this near horizon dp brane geometry in non-relativistic string theory. So an interesting thing we observed was that if p is equal to 3, so you have a d3 brane in non-relativistic string theory, then the dilaton remains constant. So we think perhaps this could give rise to a new holographic correspondence. We haven't had time to explore it yet, but we are planning to do it. And what's interesting, we think at least, is that this is really a gravity background in non-relativistic, in some version of non-relativistic gravity. So if there is a duality there, it's really a background in non-relativistic gravity and most likely some non-relativistic field theory as well. So on the field theory side, as far as I know, this field theory hasn't really been written down, but there are some studies of this limit by Ziggy and other people. But you can also play other games with this solution. You could try to think of what happens if you put a temperature, right? So you can put this blackening function inside the dp brane. So you get this, you modify the solution with this f function, and then see what happens. And I think I forgot if in the transverse part, but it doesn't really matter for this, for what I'm gonna say. So if you try to go through the same thing, then you see that after the T-duality, you get this background here. But now you cannot really, at least not if you have f different from 1, take the c going to infinity limit, because this B field is not critical anymore. So on the face of it, it looks like you cannot really have a black dp brane in non-relativistic string theory. And this we found very interesting, because how should one interpret that? Does it mean that you cannot have horizons in non-relativistic string theory? What happens if you turn on the temperature in the theory, etc.? So there's something here that we really would like to understand better. Then one can, of course, also play the same game with other solitons, such as the NS5 brain, where we did the same thing and found rediscovered a previously found solution as well. But there's also cases where if you try to do what I described, looks like on the face of it, like it doesn't work, or not the way one would expect from what I said. So one case is if you take, if you go back to the original winding mode. So this BPS momentum mode, I forgot to say that, but after the T-duality, that becomes a winding mode. So this solution with a critical B field has a winding mode. And of course, for a low winding mode, if this winding number is low and the string coupling is small, this doesn't back react. But you could imagine you turn on the string coupling and then you have a very, very high winding number and then you get a back reaction. So what happens? Well, then we, by the rules of relativistic string theory, we get a F-string soliton. So what happens now if we take C going to infinity? And this at first seems a little bit of a mystery, because if you take C going to infinity, you notice that the coupling to gravity becomes infinitely large. So how do you interpret this? Well, that's precisely a near horizon limit. So a near horizon limit is nothing but having that the coupling to a source becomes so large that in a sense the source is everywhere in your space-time. So in other words, we get the near horizon limit of a F-string. So that means that this C going to infinity limit in this case, which we previously called non-relativistic string limit, is precisely a near horizon limit. But what is the interpretation of this? Because now we have gone from, something I called non-relativistic string theory to this background here, but this background is not a geometry in non-relativistic string theory. This is a background in relativistic string theory. So is there something, does this invalidate the whole theory, even if we have that it's been shown that non-relativistic theory is UV complete and unitary? I mean, what's going on? And then we have to go back to the late 90s and think a little bit, because actually the famous IMSI paper tells us that the validity of this near horizon F-string requires the curvature length scale to be larger than the string length. And one can use the tools learned back then to translate that into a condition on the energy of the worldsheet theory, which looks like this. So our interpretation of this is that this near horizon solution, near horizon background, is a description of non-relativistic string theory, or rather the worldsheet theory of non-relativistic string theory, when the coupling is sufficiently strong. And in fact, you can see if the string coupling here would go to 0, this would become so large that for finite energy, this energy range would not really be there anymore. Or, yeah, you can play the same game with the winding number. So that's our interpretation, and we can make a further argument for this by looking at non-relativistic string theory, because an interesting thing with non-relativistic string theory is that if you consider multi-string states in the limit, thank you, you can convince yourself that since all the strings are parallel to a particular direction on which there's a winding number, and since this winding number has to be fixed, then the multi-string states are actually partitions of this winding number. And I just try to illustrate this if for the particular case of winding number equal 3. So then there's 3 cases that you have to consider. And this you can actually translate, again, going back to the 90s, to a matrix description. The details are here if you're interested. And this is nothing but what Lubos Model and Robert Dijkgraaf, who was here, and Herman and Erik Verlinde did in '97 when they found matrix string theory. So in other words, matrix string theory is basically non-relativistic string theory in type 2B flat space. This was already, I should say, recognized by several people. But here it's this is the statement, yeah. But then if you go back to Dijkgraaf et al.'s paper and consider the interactions on the non-relativistic string worldsheet, then there is this twist field operator. And you can then convince yourself that this means that the non-relativistic string worldsheet theory is weakly coupled when you have sufficiently low energies like this. And this is precisely the opposite requirement of our near horizon requirement. And of course, this is, in a sense, no surprise if you remember the lessons of what people did in the 90s. But here we sort of found this to be true also for non-relativistic string theory. So it sort of gives the non-perturbative completion of non-relativistic string theory. This also opens up, I think, for some new ideas, new things to explore, because this action here that I was highlighting in the beginning of the talk, one could actually try to find a matrix-valued version of this action, because in a sense, this action is when you only have one string, but there should be a corresponding action for multi-strings. So it should be possible to write down, a version of this action where the transverse fields are matrices. And this should give you access to a quantum geometry of non-relativistic string theory. And this would actually mean you, in this sense, maybe can go a bit further than relativistic string theory and learn about some parts of string theory that is more difficult in the full relativistic string theory. And one could also dream about combining this, for example, with this version of holography that I highlighted before. And for example, also study how holography works with an infinite speed of light. And then my last slide, I just wanted to highlight the connection to Siggy's talk, because all this is part of a broader network of BPS decoupling limits. And you can think about basically all the U-dual orbits of the DLCQ. We started doing that 25 years ago, and now it looks like we are finally trying to complete it. Especially, I want to highlight some of these two papers. There's also more, but for sure these two papers on this by Blair, Siki, and others. So there's the non-relativistic string theory for the F string. There's the BFSS. It should have been the matrix theory for the D0 brane. That's Maldaceno's decoupling limit for the D3 brane. And then there's also other cases, and then you can take multiple decoupling limits as well. And then we are hoping to make a even more systematic exploration of all this in an upcoming paper with Jan de Boer, Niels, and Siki. And then there's also another case where it seems to work a bit differently. So this Maldacena decoupling limit is in the Poincaré patch, gives you ADS shift T in the Poincaré patch. But if you think about the global patch, it's connected to something called spin matrix theory. And then things works a little bit differently with these non-BPS decoupling limits. Thank you.
Thank you very much. Are there questions, comments for Troels? Can't see any.
Thanks, Troels. So just a quick, so what kind of backgrounds do you expect for the bulk theories to have? So is there some kind of non-relativistic limit of ADS that you expect to appear?
You mean for the this holographic case or what?
For the non-relativistic holography.
Yeah. So that it's I mean, basically you have a combination of having a D3 brane, and then you have a electric field where the spatial direction is transverse to the D3 brane. So it's actually a quarter BPS state seen from the relativistic string theory. And I mean, the background I wrote was the one I showed you, but we still have to explore it. Yeah. There's another question.
No more questions?
I think Laura had a question.
No, he
maybe.
changed his mind.
Oh, okay, fine. Thanks.
Okay, let's thank Troels once more.